There was a huge amount of interest last year after the failure of the OceanGate Titan, and a spate of videos came out on YouTube, some of them very good, others, well, not so good. And there was universal criticism of OceanGate's activities, but very little constructive comment about how the project should have been handled. And now the dust has settled, I'd like to put this right, and in particular I'd like to talk about the engineering process which should have been followed. Not the technical details of the engineering, which I'd like to return to later. And my motivation for doing this is I'd like to capture the lessons which are available from this tragedy. I want to talk now about roles and responsibilities. Now, suppose we have a business idea. We want to offer tours down for the Titanic, and to do this, we need to set up an operations-focused company. We need to find the customers and operate the tours. And initially, we want to have nothing to do with the provision of the submersible. And a number of activities to do with the sub will then have to be outsourced. And how to do this? Well, there are different models. Firstly, if we can find a suitable contractor which is willing and able to charter us a vessel, that's one way to go. And this is a very attractive option because it means that our company doesn't have to change very much. We can still concentrate on our core competence. The next step up the ladder, if we can find suitable sub to buy, we purchase it. Now this starts to change the shape of our company because we're going to have to take maintenance in-house, and to do that we've got to understand a lot about the vessel, and we're going to need to start to build an engineering capability. I understand that this is where OceanGate started out, but they couldn't buy submersibles to carry the number of passengers they wanted down to the water depth they wanted, and they then decided to develop their own. Well, this changes the shape of the company completely. Look at all the activities which have had to come in-house. There are, of course, a number of outsourced activities, in particular equipment supply and manufacturing subcontracts. But what about the engineering? We could, of course, do this in-house, but you'll need to build a very substantial engineering department covering a number of specialised disciplines, and it will be a big overhead on the company, and probably far better to contract out elements of the engineering, maybe the design of the pressure hull and of some of the systems. But even to do this, we need to have significant in-house engineering capability, merely to develop the bid documents, to bid and award the engineering subcontracts and to supervise them. But also we need to have engineering input into all of these activities, which are to a greater or lesser extent engineering driven. Now, the one thing you can't do, you can't split up the design of the pressure hull. You can't have design and manufacture subcontracts for the various elements of the hull. This has to be designed as a single unit, so this is a complete no-no. Now, before we start work, the big question is whether we're going to classify the submersible or not. And to me, it's not even a question. If the sub is going to be manned, it's got to be classified by one of the ship classification societies. Now, there's a number of such societies, and the big ones are at the top of the list here. I work with several of them, and they all offer technical expertise. They're all independent, and none of them is going to let anything pass which is at all dodgy or risky. For the sake of this video, we may as well pick Lloyd's. I know them well. I've worked with them on a number of projects involving both fixed and floating offshore structures, and to my mind they're as good as anyone. Now, if you log into the Lloyd's Register website, we've got here a full list of the rules and regulations. And if we scroll down to number 13, Rules and Regulations for Construction and Classification of Submersibles and Diving Systems, clicking on this, we've got the different parts, and clicking on part 3, we've got all the design requirements for pressure chambers. Now, if we go to the page relating to the design of the pressure hull, we'll see that the regulations are actually surprisingly light. There are no formulae here, and you won't be able to design directly from these regs. However, looking, for example, at the design of the acrylic windows, they do refer directly to the ASME PVHO code. And regarding the design analysis for the hull, they say it's got to be carried out to a recognised method from a relevant and recognised international code of pressure vessel design. And although they don't mention the ASME PVHO code directly, I think that's what is implied. Now let's get to the heart of the matter by reviewing the ASME PVHO code, pressure vessels for human occupancy. Well, let's get into it, and we go straight down to clause 1.6 materials, and it's apparent that this is aimed principally at metal pressure vessels, and they say that non-standard material should be qualified for use as defined in non-mandatory Appendix D. We now go to Appendix D, which is guidelines for submission of a case for non-standard designs, materials and construction. And what you basically have to do is you have to make up a special case and submit it to an ASME PVHO consensus committee for them to approve. And what they say is that the intention is to ensure that alternative approaches are implemented with design margins and quality assurance commensurate with those set forward for recognised materials and geometries. However, it's obvious that there's a great deal more uncertainty with non-standard designs. Qualification is done on the basis of testing of prototypes, and that these tests have to be witnessed by an independent third-party agency. And now we get to the heart of the matter. Pressure tests should be conducted on a minimum of 3 full-scale prototype chambers. They should be full-size for identical construction to the end item, and that none of these chambers can fail at less than 6 times the rated maximum allowable working pressure. It goes on to give the requirements for extended duration testing and also for cyclic pressure testing. Now this formula here tells you the number of permitted pressure cycles you can use in real life based on the number of test cycles you've done. But this only kicks in once you've already done 2,000 test cycles. So that's the ASME code. I have to say that some of the requirements for qualifying a non-standard design are pretty onerous, and in particular the need to test 3 full-scale prototypes to 6 times the design pressure. Well, it may just not be possible to do that. However, they leave the door open. Firstly, they say that these are non-mandatory requirements. However, you've got to present your case. And secondly, they say that the objective is to demonstrate that with your non-standard design you can get the same level of reliability as you get with a conventional design, which has been designed to a normal factor of safety, which will be typically around 3. Now, you only use a very conservative factor of safety as a brute force and ignorance approach. You really don't understand what's going on. A much sounder approach is to do more research to understand what's going on, and so you can demonstrate that you can get the target reliability with the unconventional design and at a lower factor of safety. Now, when I say do more research, this would typically be testing a lot of scale specimens to failure and use this to calibrate your analysis model and then to use the analysis model to design the end product. Now, the ASME committee will consider a well-argued case and they will be reasonable, although bear in mind that their primary interest is safety rather than commercial considerations. A notable feature of the OceanGate Titan is the use of new technology. However, if you look at it closely, you find it's not all new. What they've done is they've taken some quite well-established technologies and used them in a novel way. And anyone who wants to know a little bit more about this, I'll refer them to the excellent review paper which was written by a team from Ifremer, published in the ASME Journal of Pressure Vessel Technology in 2016. And reading this paper, you'll see that there are examples of composite fibre cylinders being used in deep water applications going back more than 30 years. It seems to me that the novel features of the Titan are firstly the use of CFRP hull for human occupancy, And secondly, the hybrid construction with the titanium end domes and the composite centre section. Now, the inherent difficulty of using new technology is that by its very nature, it's not covered by existing codes and standards. So you can't just go ahead and use it. You've got to qualify the technology first. The technology qualification process is not just a question of running a few tests, finding positive results and saying job done, we can go ahead. It's got to be a properly planned, structured and controlled process leading to the establishment of a sufficient level of confidence to be able to go ahead with it. And there are codes and standards covering this. One such is DNV Recommended Practice A203 for the qualification of new technology, and I'll cover some of its key points now. A key objective of the recommended practice is to establish confidence in the new technology. And as they point out, confidence has a conventional meaning in statistics, but here it's used in a much broader sense to denote the confidence a decision maker can have in a new technology. And specifically, at the end of the qualification programme, he should be in a position to decide whether or not to proceed with the implementation of that technology. The way the protocol works is as follows. All of this is what's called the qualification programme, and this has 3 stages. Stage 1, concept evaluation, then pre-engineering, then detailed engineering. And within each stage, we have a qualification process, and the form of the process is identical in each case. And we start off deciding what qualification basis is, assessment of the technology, what needs to be proved, and where we need to get to at the end of this stage. And we come up with a qualification plan, we execute the plan, and we then assess the results. And we see whether we've met the target or not. If we haven't, we have to loop back again and do this as many times as necessary to meet the target. Having achieved that, we can then go on to the next stage, stage 2, and likewise on stage 3 until we meet the final milestones, at which stage the qualification programme is completed. Well, this is starting to take shape. We've already decided we're going to go for class approval. We've got some technology qualification to do, and we've got a protocol for that. And we're going to design these submersible in accordance with the ASME code. But there's still something missing. How do we know we've done the job right? Or to use an analogy from a recent example, how do we know that the bolts of the aircraft door have been fitted? Well, of course, the answer is you've got to have an all-encompassing quality management system, or QMS. Now, by far the most widely used international standard for this is ISO 9001. And I'll point out the use of an ISO 9001 QMS is a requirement of the ASME code. I'm not going to give a general rundown on the operation of an ISO 9001 quality management system. Plenty of information out there on the internet. But I will pick on a couple of key aspects and I'll let people draw their own conclusions. Now, a cornerstone of the system is the requirement for leadership and top management support. And this typically takes the form of a one-page policy statement signed by the chief executive and the other directors. And this policy statement is implemented by the line management. It's not just seen as a function of the quality department. And any softening in top management support and the whole system falls apart. And in particular, what you can't have is the chief executive going around saying that the compliance system, it costs too much money and it's a waste of time. You've got no chance. Now, to give an actual example, let's look at, say, the quality control of the procurement of raw materials and manufacturing into a CFRP component. Now, the goods would be bought from a suitably qualified manufacturer running his own certified quality management system, and they'd be bought against a very detailed specification. They would be supplied with full manufacturing records and test data, and there would be a release inspection before they left the factory. They'd be transported to site, and there will be a goods inward inspection and any non-conforming items put into quarantine to ensure they couldn't enter the manufacturing chain. They'd be stored under the specified conditions, temperature, humidity, whatever, and this would be continuously monitored to ensure that these conditions were met. They'd be taken out of storage for manufacturing. Full traceability would be applied, so you'd know which batch of raw materials go into which item. And they would be manufactured against a detailed method statement, and all of the relevant parameters would be measured. So for filament winding, you'd obviously measure the filament tension, the mix, the temperature, whatever. The work would be done by a suitably qualified technician with a trade cert. And then when that was finished, they'd go on for the various finishing processes, curing or whatever. At various points in the production process, there would be hold points and NDT would be performed. I'm not even going to get into the NDT, which is a huge subject in its own right. A lot of concern has been expressed about the way that the titanium and composite shells are bonded together. Now, the key to good bonding is surface preparation. So typically, the surfaces would be prepared in accordance with AMPP standards. Firstly, there would be surface cleaning using either solvent or other chemicals, then grit blasting to white metal standards, and then probably a further level of treatment as recommended by the epoxy manufacturer, probably using laser texturing. And something similar would be needed on the end of the composite shell too. And having got the surfaces clean, you then need to take suitable precautions to keep them clean, and ideally to do the bonding as soon as possible to avoid the risk of further contamination. Now, all of this is in marked contrast to the apparently shockingly careless way in which these joints were made in real life. Now, the cost of running an ISO 9001 quality management system is of course quite high, although the mantra in quality circles is that quality is free, the cost of the system being more than offset by the savings in repair and rework. That may be debatable. However, the fact is that companies with good quality management systems tend to prosper. And what is undeniable is that the cost of running the system is infinitely lower than the cost of having a major incident where there are fatalities, companies destroyed, and major litigation is launched. We now come to a subject which is very close to my heart. I've already shown that owing to the type of business model which OceanGate adopted, engineering lies right at the centre of their operations, and that a failure in the engineering department would likely lead to failure of the business. Now, any engineering department, its primary duty is to produce designs which are fit for purpose, they're safe, and they're also economical solutions to the design requirements. However, the secondary duty is to ensure that the design intent is implemented by the rest of the organisation. And it doesn't matter how you look at it, it'd be very hard to argue that at OceanGate they've failed abysmally on both of these fronts. Before we try to get to the bottom of what happened, I'd like to spend just a couple of minutes looking at how a typical multidisciplinary engineering department operates. Now, let's take the example of quite a large multidisciplinary engineering project. This was an actual project in the Middle East, and we got the engineering department here controlled by the engineering manager, and down here we've got the various disciplines, and if you count them up, there are actually 11 individual disciplines. Now, within each discipline you'll have the junior engineers who tend to be working on the computers, you'll have senior engineers who've got a bit of experience, and you'll have a lead engineer, and he controls his discipline. He tends not to take much interest in what's going on outside of his discipline, but if things aren't right in his discipline, he will holler. Now, the engineering manager will have started off as one of the discipline engineers. He will become a lead engineer. He will have shown competence in his discipline, but he will also have shown that he takes interest in what goes on in the overall project, and he will acquire a working knowledge of what goes on in all of the other disciplines. And when he gets promoted to this position, this is a managerial position, not a technical position. And his main duties, well, he's got to be a very good man manager, he's got to be an excellent communicator, He's got to establish good working relationship with other managers at his level and with his boss. But within the department, he's got to ensure that the engineering process is followed. So what did the OceanGate engineering department look like? Well, of course, we don't really know. We do know it's controlled by an engineering director, and there are images of him smiling proudly into the camera as the fateful bonding operation was being performed on the Titan hull. And we've heard a lot about $15 an hour engineering interns, mere children in engineering terms. What we haven't heard about are the mid-level senior engineers and lead engineers. And maybe these were the middle-aged white guys who were so despised by the late CEO of OceanGate. Now, I've known dozens of these guys in my engineering career. They tend to be conscientious, hard-working, and take a lot of pride in their work, and they wouldn't tolerate any nonsense affecting the quality of their work. Maybe they just weren't there. What I can say is that you can't have an engineering department where you've got an engineering director at the top going down to interns at the bottom. This would be completely dysfunctional, and any designs they produce are likely to be deeply flawed. Next point. We hear that the late chief executive of OceanGate was an overpowering and bullying individual who pressured his staff to cut corners in order to reduce costs. Now, in our working lives, we've all been subject to pressures to do the wrong things from time to time, but you've got to resist. Now, there seem to have been a couple of such cases at OceanGate. We hear that chief accountant was being asked to act as a submersible pilot. She didn't feel qualified for the job, so she left the company. And the operations director, who published a negative safety report on the Titan, he got fired and got sued by OceanGate. But at least they did the right thing, and they should be commended for that. Now, as engineers, there are things that we are and are not allowed to do. And any professional institution we belong to will have a code of ethics which we are obliged to adhere to. And in the code of ethics, a high priority will be given to the health and safety of anyone who might be affected by our work. And in most jurisdictions, there's a general duty of care towards the public. And the OceanGate engineering personnel had been subject to this likewise. Now, we violate these obligations at our risk. The very least that's likely to happen is to be expelled from one's professional institution and to lose one's livelihood. But in more serious cases, you can be subject to criminal prosecution. So what actually happened in the OceanGate engineering department? Well, of course, we don't really know. The kindest interpretation will be that the department was so dysfunctional that they didn't realise the inadequacies of the design they'd put out. But that would be a simply incredible level of incompetence. The other more sinister interpretation is that they buckled to the pressure from the chief executive to cut corners, and they put out a design knowing it to be deficient. Now, that would be deeply reprehensible, and in my opinion, those responsible should suffer the consequences of their actions. So the engineering process, which I've proposed, looks something like this. Technology qualification to a recognised protocol, design of the sub to a recognised design code, leading to classification by one of the ship classification societies, and all underpinned by an ISO 9001 quality management system. This isn't the only route one could have followed. One could, for example, have designed the submersible to the US Navy SUBSAFE program. Now, SUBSAFE was introduced 60 years ago after the loss of the USS Thresher, and no submarine which has been designed in accordance with SUBSAFE has ever been lost. It's been very successful. It's a wide-ranging quality management program, a lot of overlap with ISO 9001, but obviously particularized the requirements for the US Navy. But they do cover some areas which aren't even touched upon in the ISO standard, and one of them is cultural issues, and they identify as a particular problem Ignorance, arrogance and complacency. Very prescient. Makes you think, doesn't it? In summary, if the OceanGate Titan had been designed in accordance with a sound engineering process, I think we can be sure that the disaster would never have happened. I also think it would never have seen the light of day. The development program would have taken longer and costed a great deal more, and I think it was simply beyond the capability of a company the size of OceanGate. A great pity, really.